In this module, we're going to continue the previous lecture on language models, and we're going to cover specifically some more sophisticated smoothing schemes and discounting schemes, okay, for Ngram language models. So this is a recap from the previous module. So we had looked at this challenge of unseen Ngrams. How do we deal with unseen Ngrams at test time that never appeared in your training corpus, right? If there was no smoothing, then the sentence will automatically be assigned a probability of 0 because these are zero count events. We look towards what are known as smoothing methods or smoothing techniques. And the philosophy behind smoothing methods is that you want to reserve some probability mass away from the seen Ngrams towards the unseen Ngrams, and then appropriately redistribute it across the unseen Ngrams. Okay, so the simplest smoothing scheme was add one or Laplace smoothing, where you just add one to all the counts and then appropriately renormalize the distribution. Let me just add my pen. Yeah, so this is the renormalization, and here capital V is the vocabulary size. So here's the here's what add one smoothing does, and here's what it does to the resulting bigram probabilities. So here one problem that we immediately highlighted was that events which used to be fairly high probability events, now they've lost a lot of mass. So the stealing from the rich, giving to the poor analogy, it's kind of been taken to the extreme with add one smoothing. So a lot of mass has been driven away from the seen Ngrams towards the unseen Ngrams. And this is not really desirable because, especially since these are maximum likelihood estimates, the ones which are already pretty high and have been estimated with lots of seen Ngrams, you don't want to mess with those numbers too much, right? So, and here as which is the size of a vocabulary grows, this problem becomes more and more dire as to how much mass is going to be moved away from the seen Ngrams towards the unseen Ngrams. All right, so a small kind of a band-aid fix to this was to do add alpha smoothing, where instead of 1, you actually add some alpha which is less than 1 to each count. Okay, but here you would have the challenge of choosing alpha. How would you go about appropriately choosing an alpha? Smoothing could also be viewed as discounting, and this is important when we discuss the first scheme, which is good Turing's discounting scheme. So discounting, it's just a different view of smoothing. You can write the new probability with Laplace smoothing as a discounted count in the numerator, which is denoted by pi star divided by the total number of the unigrams, right, corresponding to wi minus 1. And so pi star can be written as follows. Okay, this gives you, with this you exactly retrieve the probability of the bigram with Laplace smoothing in place. But here you now have this discounted count, which is denoted by pi star. All right, and so this is what the discounted counts would look like after Laplace or add one smoothing. So what are some of the problems with add alpha smoothing? One, even though this is certainly better than add one smoothing when alpha is less than 1, it's still taking away too much probability mass from seen Ngrams towards the unseen events. It's not really discounting high counts and low counts correctly. And as we mentioned before, alpha is tricky to set. The simplest way to do this would be to treat it as a hyperparameter and use a validation set. Okay, how do we kind of do this in a more principled way? So the first proposal is the good Turing discounting scheme, which was proposed many decades back, but it's a quite an elegant scheme. So before I even describe how good Turing estimation works, here's a table. In the first column, R is the count of tokens in a large corpus. Okay, so here 1, 2, and so on means a particular token appears once, appears twice, and so on. N sub R is the number of bigrams with R counts. Okay, so I have 2 million bigrams. So here they say bigrams in this original paper where I got this table from, it's bigrams. You can think of them as any tokens. Okay, so NR is the number of tokens with R counts, okay, which just appear once. So there are 2 million bigrams which only appear once. There are 4 lakh bigrams which only appear twice, 2 lakh which only appear thrice, and so on. Okay. Now R star is your think of this as, again, it's a discounted count. Okay, so this is the actual count in your corpus. R star, like we had the pi star earlier, is a discounted count, and here R star is just something which was estimated as a proper count on a different held out corpus. Okay, so people looked at what is kind of this R star value when estimated on a different held out corpus, which is different from the training corpus out of which these statistics were derived from, which correspond to the first two columns. Okay, and those values were as follows. So R star is 0.448, 1.25, 2.24, and so on. So you can see that the discounted counts are strictly lesser than R. Okay, which is not surprising because this is a discounting technique after all. So you're going to move away some of the mass away from these seen engrams. But uh, look at how it compares with the R star when you use add one smoothing. Okay, so if you use add one smoothing, here are what the discounted counts look like for these original kind of engrams, which were appearing with the count of 1. Now they will be appearing with a count of 2.8 into 10 raised to minus 11. Okay, now here the vocabulary size is very large, which is why you see these really, really small values in the add 1 R star. So you can see that these values are really large kind of overestimates, right, of the fraction of unseen events. And the good Turing, this R star, which was actually estimated on a held out set, you can see that it's lesser than R, but it's much more controlled, right? So the good Turing estimation, you don't assume access to an actual held out set, because that might be kind of an additional resource which you may not have access to. So good Turing estimation, it uses the observed data, and the observed data is what you use to estimate these numbers, right? The first two columns of this table. You stick to the observed data that you have, but try and use this observed data to predict how to go from R to the R star, which you would have got on a held out set. Okay, so in short, good Turing estimation is based on finding the expected frequency in a held out set of words based on counts which are estimated from an observed set of words. Okay, so now let's step through the good Turing estimation process one step at a time. And the intuition for good Turing estimation comes from leave and out validation, okay, which you might have encountered in when you've learned about cross validation. Now, as before, NR is the number of words or tokens or bigrams that occur R times. Now, say that you're given a set of n word tokens. This is your observations. Okay, you have n word tokens. I'm going to split it into a training set of n minus 1 samples, and then one sample is my held out sample. I'm going to repeat this n times so that all these n samples are going to appear once in the held out set, as the held out set is going to appear once. Okay, so there are n such trials where I'm going to make these splits of into n minus 1 training samples and one held out sample. Now here's the first question. In what fraction of these n trials is the held out word unseen during training? So I'm just going to go ahead and give you the answer, but when you're watching this lecture, take a few minutes to kind of think of this on your own before you look at what the answer is, right? So the answer would be n1 by n, because I'm asking about the fraction. So there are n trials. Of these, I'm asking what is the fraction where the held out word is unseen during training, okay, which means that the held out word only appeared a sum total of once, right? And so when it was in the held out set, there are no instances of that word appearing in the training set at all. And what is the number of such tokens? We know it's n1, because n1 is the number of tokens that occur exactly one time, right? So this is the fraction of the n trials where the held out word is unseen during training. Now, here's the next question. In what fraction of the n trials is the held out word seen exactly k times during training? Okay, and here the answer would be k plus 1 times nk plus 1 by n. And this can be motivated further. So if you think about how many words or tokens there are with a training count of k, there are approximately nk such words. Okay, and why do I say approximately? So say that some sk is the set um, of all word types the set of all word types, each of which not appears occurs k times. Okay, and so then your nk is essentially the size of this set sk, right? Because nk is the number of words that occur k times. Now, in any trial, depending on whether the held out word is in sk or sk plus 1, right, or not in either of these cases, then the number of words with the training count k will be either nk minus 1 or nk plus 1. Okay, which is why we are saying it's approximately nk words with training count k. Okay, all right. So we predict from the held out set that there are k plus 1 times nk plus 1 words that are seen k times during, exactly k times during training, right? Um, so what is the probability of each of these words being chosen as a held out example? So it would be this earlier fraction, because this fraction represents the number of events where the held out word is seen exactly k times, right? And then here you know that there are approximately nk words with a training count k, so you would divide further by nk. Okay, so now this is the probability of each of these words being chosen as a held out sample. Okay, so then what is the expected count of each of the nk words in a corpus of size n? Okay, so that we're going to denote by k star. And so then it would be, so here you have this probability. This essentially, um, so from this, you can see that the expected count is, once you kind of omit this n out, right? So the expected count of each of the nk words in a corpus of size n would just be k plus 1 times nk plus 1 by nk. So this is exactly what the good Turing estimation is, because it's trying to find an expected frequency in a held out set of words based on counts like nk plus 1 nk, which you are estimating from an observed set of words. So your observed set of words are your n word tokens, right? And you're saying I want to give an estimate, an expected frequency in some other held out set, but all I have available with me now are all these observed sets of words. What would be a reasonable kind of estimate I can make? Okay, and that is exactly what this good Turing estimation gives us. So here we've derived that to be k plus 1 times nk plus 1 by nk. So how do these good Turing estimates look? So here, this is very similar to the table we showed earlier. So showing you frequencies of bigrams from 0 to n. Okay, so here you can see that, and this R star held out was actually estimated on a held out set. R star GT is the good Turing estimate based on the observed set of counts. So you can see that R star GT is almost the same as R star held out for all these initial values of R, right? So this is a fairly good approximation of these discounted counts if you actually had access to some other held out set. Yeah, so this is the final expression for an adjusted count R star according to the good Turing smoothing scheme. So for any Ngram that occurs R times, the adjusted count R star would be R plus 1 NR plus 1 by NR. So here's, and so more importantly, for the unseen events, which means you're looking at theta of 0, what would be your good Turing smooth count? It would be N1 by N0. Okay, that's the smooth count for unseen events. So here's a simple example. You have, these are all your kind of observed word tokens. The question is, how likely are you to see guava? Okay, so the good Turing estimate would be theta 1 by n. right? Because I'm looking at guava. I want an adjusted count for guava, okay, which appeared only once. So how do I compute theta 1? Theta 1 we know is 2, which is r plus 1, into n2 by n1, right? So what is n2 here in this data set? Um, you have papaya appearing twice, which means there's just one of them. So that's 1. And then what is n1? N1 is you have melon, guava, and pear, tokens which appear only once, and there are 3 of them. Okay, so N1 is 3. So that gives you 1 by 3 times 2, so that theta 1 is 2 by 3, and divided by n, which is the total number of tokens. Okay, so this is the good Turing estimate. The probability of guava appearing next, according to the good Turing smoothing scheme. Okay, so one issue with good Turing estimation is that once you move to larger R's, you will run into kind of many instances of nr plus 1 being 0, right? And this is fairly common for high R's, high values of R, that you see these kinds of holes in the counts of counts. Okay, and so this would subsequently lead to theta R also being set to 0 because nr plus 1 is 0. So there are a bunch of small kind of solutions to account for this. One is you can discount, have a threshold k, and you say that we only do discounting for small counts of r which are less than equal to k, and the discounted count is just the same as r for every r greater than k. So this is, one is somewhat semi-solution, not terribly satisfying. Another solution is just you apply a smoothing function, okay, using kind of a best fit power law or even kind of linear regression. Just smooth this NR once the counts start getting small, so that your you won't have instances of nr plus 1 being 0, but they will get set to some non-zero value because of this smoothing. Okay, so that's another stopgap solution. But that's okay. I mean, we just want to kind of, for you to get this high level understanding of what the good Turing estimation scheme does. Okay, so good Turing smoothing is now allowing you to discount probability mass to unseen events. So now let's think about how we want to do this distribution across unseen events. Okay. Um, so let's look at a very common idea, two common ideas in language models, which is one of back off and the other is one of interpolation. So the idea of back off is just that when you don't have counts in a higher order context, okay, you back off to a context which is smaller in size. So you use lesser context to generalize for larger context that the model doesn't know enough about. Okay, so here, what is the back off idea? Say that you're trying to build a trigram model. If you're not going to see trigram counts at all for certain sets of trigrams, okay, then you're not, so clearly the estimate is that the actual count of those trigrams is 0, right? There's no evidence for the trigram in your training data. Then you use bigram or unigram probabilities. So you strip away a little bit away from your history of the word context. So you're saying, okay, I actually don't have both these words in my history. I'm not getting enough counts for them. So let me take away one word. Let me only look at the previous word and then see whether I have any bigram probabilities. If I don't have that either, then you just back off further to unigram probabilities. Okay, so that's the kind of overall idea of back off. And in a few slides, we will formally talk about what a back off probability distribution for an LM looks like. And interpolation just means like you would kind of interpolate two probability distributions. It's just talking about mixing probability estimates coming from trigram models, bigram models, and unigram models. Okay, so what would interpolation look like? So we can look at the simplest scheme, which is linear interpolation. So you linearly combine the probabilities from different Ngram models. Okay, so here is one example. If I'm trying to find the probability of Wn given some Wn minus 1 and n minus 2 and minus 1, then I'll actually look at the trigram probability of Wn given Wn minus 2, Wn minus 1. I will look at the bigram probability, okay, which is, I'm going to strip away some of the context and look at only having seen n minus 1 in my context. And then finally, I have the unigram probability. And all of these three probability terms are scaled by lambda 1, lambda 2, lambda 3, which should all add up to 1. So these are your mixing coefficients. So how do you set these lambdas? You can first estimate these Ngram properties in a training set, and then you want to search for lambdas that maximize the probability of a held out set, right? So this can be a hyperparameter search. This can also be kind of learned using EM. Okay, there are kind of different schemes in which you could set these lambdas, okay, for linear interpolation. Okay, so that we're not going to spend a lot of time on. We're going to talk a little more formally about back-off smoothing. Okay, back-off smoothing, also referred to as Katz smoothing, Katz back-off smoothing. Okay, so here again, like I mentioned earlier about back-off, the idea is that if you don't have evidence of kind of higher order n-grams, then you back off to lower order n-grams until you find evidence. Okay, so if you don't find trigrams, use back-off probability of bigrams. If you don't have bigrams, use back-off probability of unigrams. So let's now formally define what a bigram model with Katz smoothing or back-off smoothing will look like. So before that, let's first define psi of wi minus 1 as the set of all w's such that the counts of wi minus 1 w are greater than 0. So there is evidence for bigrams of this sort, wi minus 1 comma w. Okay, and this is the set of all such w's. Now, given that this is a definition of psi, what is a bigram model with Katz smoothing? So a bigram model of Katz smoothing can be written as follows. There are two clauses. So you're trying to find, this is for a bigram, this is a bigram model, right? So you're trying to find the probability of wi given wi minus 1. So you first check whether wi belongs to psi of wi minus 1, meaning that I do see non-zero counts of the bigram wi minus 1 wi. Okay, if that is the case, then you would just resort to this expression, for which now should be familiar to you, which is just the standard expression for estimating a bigram probability, except in your numerator you have a discounted count. Okay, you don't have the actual count. Okay, and now what do you do if wi does not belong to psi wi minus 1, which means you don't see this bigram, there are no counts for this bigram. Then you back off, here is where you back off to the unigram probability corresponding to wi, and this is scaled with what is called a back off weight assigned to every wi minus 1. So here you see alpha is a function of wi minus 1. Okay, and here alpha can be defined by using this following expression. Okay. All right. So here is your entire smoothed probability distribution. Let's try to kind of step through this. So how did we kind of come up with this expression for alpha wi minus 1? Now, here, this is discounted, right? The pi star, which is now highlighted in yellow. So it's discounted, which means there is some probability mass that has moved away from the seen in grams. And now this leftover, so what is this leftover probability mass? It would be whatever is in this numerator of alpha wi minus 1. So that is 1 minus the sum over all w that belongs to psi wi minus 1, pi star wi minus 1 w divided by pi wi minus 1. Okay, so look at what this is saying. So I'm going to sum over all the w which belongs to this set psi wi minus 1. Okay, I'm going to compute the entire the sum of all these probabilities, and then 1 minus that would be my leftover probability mass, right? So this is my leftover probability mass, and this I need to kind of distribute over all those wi's which do not belong to psi wi minus 1, right? And so then so that kind of distribution, which is proportional to the probability of Katz of wi, is ensured by this term in the denominator, which is I'm going to sum over all wi which does not belong to psi wi minus 1, the unigram probability of all such wi's, okay, which do not show up in psi of wi minus 1. So now you should see, okay, here we obviously want the sum of probability cats wi given wi minus 1 when you sum over wi minus 1, sorry, when you sum over wi, you want this to be 1, right? So you want this entire kind of distribution, these values should sum up to 1 when you sum over all wi. And so this you can split into two summations, one when wi belongs to psi and the other when wi does not belong to psi. And these, you can see that, this ensures that this kind of normalization of all these cats probabilities will sum up, the normalization holds, okay, that it will sum up to 1 when summed over all wi, which is exactly what you want from a properly normalized bigram distribution. Okay. Next, we'll very quickly look at a simple discounting, simple interpolation scheme. So here, stop sharing. So end it immediately. Next, we look at an interpolation of language models along with using a discounting scheme, which is much simpler than the good Turing discounting. And it hinges on this kind of very simple observation. So if you look at this table, again, as before, here you have the counts and then you have the number of tokens which appear this many times, right? R times. So here, theta of R is the discounted count according to the good Turing smoothing scheme. So if you look at, so what someone observed is that for R greater than 0, if you look at these numbers and theta R, it looks like it's R minus some constant, right? Approximately, at least for small values of R, which is kind of an absolute discounting scheme without even computing the NR plus 1 and NR to compute theta. So this was kind of motivated by good Turing, but then what was observed that maybe you could just subtract a constant from the non-zero counts to get the discounted count, and that wouldn't be too bad as well. So this is the kind of absolute discounting scheme, okay, which is essentially just this, that you discount your actual count with a constant d, and then of course if you end up with a negative value, then you just reduce it down to 0. And usually these discounting schemes are always accompanied by either interpolation. So here the interpolation is coming by this particular term, so where you're interpolating with a lower order unigram model. So it's either, so these discounting schemes are either accompanied by interpolation or by back off, as we saw in the previous set of previous slides, right before this particular scheme. And this is the last technique that I'll talk about, which is the Kneser-Ney smoothing technique. This is the most kind of commonly used smoothing technique for Ngram language models. So even if you look at SRILM models, KNLM models, what they would suggest is to use Kneser-Ney smoothing, okay, which empirically has been established to work quite well across various settings. So what is the Kneser-Ney smoothing technique? So this is our absolute discounting technique. Okay, so this is the Kneser-Ney technique, and here is our absolute discounting interpolation-based model, right? So I'm just trying to kind of show you the main differences between the absolute discounting smoothing technique and the Kneser-Ney Kneser-Ney smoothing technique. You'll see that the first term is identical, where you have a kind of absolute discounting, but the second term is where the main difference lies. Instead of just the unigram probabilities, I'm defining this kind of new probability, which is referred to as a continuation probability. And so let me now elaborate on what that means. Okay, so consider the following example, which is just say, today I cooked some yellow curry. Okay, and the word of interest is curry. And now suppose the count of the bigram yellow curry in my corpus is 0. Okay. Now if I wanted to compute the probability of any word given yellow using the absolute discounting scheme, then the first term reduces to 0, and then I'm left with the second term, right, which is lambda corresponding to yellow times the probability of the word, the unigram probability of the word. Say that I'm working with a corpus which is all about the Silicon Valley, okay, which means I'm seeing San Francisco appearing many times in the corpus, and curry by itself is not a very common word in my training corpus. Okay, so the unigram probability of Francisco is much higher than the unigram probability of curry, and you can see where I'm going with this. Okay, so which means that this would contribute to this particular probability that I'm computing, right? Except we know that Francisco is not very common as a continuation because it only follows San, right, mostly, as curry is. So curry is a word which accompanies many other words. Okay, so curry can come with red curry, potato curry, chicken curry, whatever, right? But Francisco by itself is not as common as a continuation because it mainly only succeeds the word san, right? So instead of just considering the unigram probability of the word, I should use the probability of the word being a continuation. Okay, so I shouldn't just consider the unigram probability because such biases might creep in. Depending on my corpus, I might have certain unigrams which kind of get inflated just because of the nature of my corpus, but and which may not actually serve me well eventually. So I should consider the probability of the word being a continuation. Okay, and that should take precedence. That is the main kind of philosophy behind Kene-Zernay smoothing. So now we can define what these terms would evaluate to. So this continuation probability of a word wi would be the size of the set, which I'm defining as phi wi, which is all the wi minus 1s such that the bigrams wi minus 1 wi are all greater than 0, have a count greater than 0. Okay, so it's the size of this set phi, which is defined as follows for wi, and then you normalize it, okay, in the denominator by looking at the size of b, where b is all bigrams of type for over all wi minus 1 wi such that the counts of these bigrams are greater than 0. Okay, so that's the normalization. And the numerator, I'm only looking at for a wi, what is the size of phi I, where size of this phi wi is the size of the set of all the words which can precede wi with non-zero count in my corpus. Okay, so that's the continuation probability. And that's exactly kind of what intuitively we meant from the previous example, right? And that's exactly what we wanted the continuation probability to capture. And this lambda will be the kind of your discounted mass. So that's d by probability of wi minus 1 times the size of psi wi minus 1 from before. Okay, so remember we had already defined the psi wi minus 1, which is all the wi such that wi minus 1 wi has a non-zero count, greater than 0 count. Okay, so this is now correctly normalized such that if I sum over all wi's, this will sum to 1. Okay, this quantity, probability of kn of wi given wi minus 1. So this is the Kene-Zernay discounting scheme. Yeah, this is I'm just multiplying all these terms which we just derived for the continuation probability and the lambda value. There's an alternate view of Kene-Zernay smoothing which I kind of present to students and might be easier for you to think about. I mean, the other one, if you're already on board with, I mean, this is just one more way to think about Kene-Zernay smoothing, which is as a mix of bigram and unigram models. So if you consider a bigram AB, let's think of it as being generated in two ways. Okay, which is that I saw the context A, so then I'm maintaining that context in my history. So this is a finite state acceptor, and then I produce an output B. Okay, so now I'm going to remember my context B, right? So this is the first way in which a bigram AB could be generated. That is, I'm in context A and I output B, or I'm in context A, but then I forget the context. Okay, I see some other token. So I forget the context A, and then I output B. Okay, so I'm going to denote this path as A epsilon B. Okay, so for each bigram AB in a given set of bigrams, let me assume this is the notation I'm using. Let me assume that D sub AB of its occurrences, of the biagram's occurrences, were produced in the second way, where I reach a context corresponding to A, then I actually forget that context, and then I output B. Okay, rather than directly outputting B from the context A. And so here's my, let's assume this and move on and derive the Kenesanet smoothed expression. So let's assume that, so pi AB is a count of my bigram AB. I'm assuming pi AB minus DAB occurrences are kind of following this path. Okay, and DAB occurrences are following this path, which is A epsilon B. Okay, so that they totally sum to pi AB. Now, the probability of B given A, right, would just be the number of occurrences. So I'm essentially considering kind of the probability of this transition being traversed. So the probability of B given A is pi AB minus DB divided by pi A, right? This is just the relative count. Now, the next is probability of epsilon given A, right? So what is the probability of this particular transition being taken? So the probability of epsilon given A would be the sum over all y day, right? Because here day, again, recall, is the occurrences corresponding to the path A epsilon y, right? And so if I sum over all such paths, then that kind of gives me the numerator term, which is how often do I step out of this state which remembers the context A and then moves to a state which has forgotten this context. So that would be all sum over all y of day, right? And in the denominator, I have again the unigram probability of A. And how about the probability of B given epsilon? The probability of B given epsilon is, again, in the numerator, similar to the previous probability, I have summation over all x dxb, right? Because I'm moving to B, which means I'm eventually going to be remembering the context B. So, but I could be coming from any other x, right? So I need to sum over all x dxb in the numerator divided by in the denominator, because it's b given epsilon, I need to sum over all xy dxy. Okay, so that's what appears in my denominator. So what is my Keneser-Ney smooth probability? It would be probability of B given A plus the probability of epsilon given A times the probability of B given epsilon. So I'm essentially looking at summing over both these probabilities. Okay, and so what would this kind of concretely work out to? Let's assume for simplicity that dxy is equal to some constant d for all bigrams xy that have some non-zero count. Okay, so and this is actually without laws of generality. We can do this. We can assume that they all appear at least d times, and that's perfectly kosher. So if I take all my dxy's to be d, then this summation over all y day would just be d times the size of psi a. So remember, so the definitions of psi, phi, and capital B are from the previous slide. So psi a is the set of all y such that pi ay is greater than 0. And similarly, capital phi and b, capital B are also defined. So summation over y d a y would be d times the size of psi of A. Summation over all x dxb would be d times the size of phi of B. And the summation over all xy dxy would be d times the size of B. Okay, so if I just plug these into my expression for the Kneser-Naismith probability, it would just be, what is the probability of B given A? It's this expression. And of course, you add this max so that this doesn't become a negative value, plus the D times, and then you have probability of epsilon given A times probability of B given epsilon, right? And so you'll see that all these quantities show up. So you have size of psi A, psi of A, size of phi of B, and the denominator you have pi of A, and then you have the size of B. Okay. So this is another alternate view of Kneser-Ney smoothing. Okay, so do kind of go back and make sure that all these expressions are clear in your mind, or we can address this during one of the live sessions. Now I want to come back to a representation of Ngram models, which we briefly looked at in the last lecture, where we showed how an Ngram model could be naively represented as a weighted finite state acceptor with v raised to n edges and v raised to n minus 1 states, okay, where n is the order of my Ngram model. Right, and so we explicitly looked at kind of constructing this machine for this particular example, and we said this is not really practical when V is large. And back-off language models are our friend here. Okay, when we don't actually have counts for all the kind of trigram models, we don't really need to represent all of these states and edges. We can just resort to a back-off language model, and a back-off language model would look something like this. So here you're in state AB. You're transitioning to state BC. So this is for a trigram model. So here, the symbol which you will be consuming is C, and the weight is probability of C given AB. This is like in the previous example that we have seen. Now here's the back off. So say you're in state AB, okay, you can back off on epsilon to a state which now forgets A and only retains the history B, just the previous one symbol context B. And the weight, corresponding weight is alpha AB. Okay, so remember from the cat's back off scheme, you have an alpha quantity, right, which is used to scale the lower gram model probabilities. So that alpha kind of shows up here in this transition. And once you're in B, again, you can go back to BC by consuming C and looking at the bigram probability of C given B. Here again, you can back off from B to a state which now remembers nothing, no context. And then again, on seeing C and the corresponding weight being the unigram probability of C, you can move to a state which remembers C. From here, again, you can back off to C, meaning that now you don't remember the B that you saw 2 steps back, but you only remember C. Okay, so this is what a back-off language model would look like in a finite state acceptor form. Okay, these are the corresponding transition weights. So with that, we'll wrap up Ngram language models and different kind of popular smoothing techniques, discounting techniques relevant to Ngram models. We'll revisit language models when we talk about recurrent neural networks. So with RNNs, we don't have to restrict ourselves to kind of limited word histories as we have to do for Ngram language models.